towards the 5G network. So we will be focusing on the 5G based network. So now this will be the basic outline that as it is a faculty development program, so various types of faculties from different domains will be there. So for them, it to make it easy, I have put like, first we will introduce our topic, then we will discuss about some RF basics like S parameters, and then the basic MOSFET configuration for impedance matching, then power amplifier, which is the topic which has different type of logic like linearization and Doetry amplifiers. Okay, so now as we all know that the RF evolution is going from 1940 to till date. So at that time it was like car based car phones are there. In 1970 the first handheld cell phone has been introduced. Hello, is I am audible or not? Hello, hello.
Yes, sir.
Yes,
Yeah,
audible,
I am
audible, sir.
audible or what?
Yes, sir. Yes, sir.
Thank you, thank you, thank you. Yeah. So the change has been from 1G to the 5G, and next is in 6G. The frequency band of 6G is 95 gigahertz to 3 terahertz. So those are also evolving nowadays. So this is the basic RF communication basic, that a transmitter side is there, in which the drive antenna with high power levels are there, which is like power amplifier driven antennas are there. And in the receiver section, it has to sense a very low signal. For this reason, antenna based LNA, low noise amplifiers, are there. So both the sides amplifiers are there. One is your power amplifier in the transmitter side, and in low noise amplifier in the receiver side, but the functionality of both the amplifiers are totally different. So one functionality is in the power amplifier is that it has to drive higher power, feed higher power in the antenna, so that the message can be sent from one side to another side. Another section in the receiver section, the low noise amplifier functionality is very low noise, very low signal is coming, then also it should able to amplify that signal and take out the essential message data. So for these thing, the baseband signaling processing is also a big introduced. Like in power amplifier, up converter is utilized in the baseband signaling, and for a low noise amplifier, a down converter or a demodulator are utilized to reconstruct the signals or the masses. So this is the basic thing, basic RF configuration. Now in today's topic is basically the power amplifier design based on CMOS design. So now we can generically divide the RF receiver into four sections. Like one is your microwave design, which is dealing with the antenna and the passive circuits like isolator, power dividers, and power couplers and circulators. These are the microwave design, which is designed on the PCB board based on your micro strip lines. So and then after that, the RF power circuit design is coming into picture, where the power amplifier is there, and that is connected with converters or the modulators, and the low amplifier is there, which is connected to the down converters or the demodulators, and both things are synchronized by the oscillators, which are giving a frequency, desired amount of frequency by which it is synchronized. So then after, the analog circuit designs are there, in which the analog to digital converters are there, or digital to analog converters are there. These all known as baseband processing. Then comes the digital baseband processors. These baseband processors you can easily design FPGA based processors can also utilize to transmit some data from one end to receive some data in the another end. So this is the basic four subdivision of your RF transceiver design. So basically, we are dealing with the RF circuit design, which is based on the CMOS design. As the required frequency are growing much and much higher, we are shifting from CMOS to the 3-5 semiconductors like gallium arsenide, gallium nitride, because their mobility is very higher. If the mobility is higher, then the frequency of operation gets higher. So from the material characteristic point of view, they are very good with the circuit design. So now these signals are up converted or down converted at transmitter and receiver section by an oscillator controlled by frequency synthesizer, like to synchronize both the things. Now if we are seeing the evolution of the mobile wireless communication, then the evolution starts from 1G to the 5G network. So it is like from 1970 to 80s, the 1G has been deployed, and it is very much used, but the speed was very less, means the data rate is about 14.4 kbps, and the technology is an AMS, because we are only dealing with the voice signal transmission. After that, the 2G comes, which is like we are including the voice and the text messages. Then comes your mobile internet, which is GPRS, which can be known as edge technology also, 2.5G, or a edge technology. Then comes 3G, which is like a UMTS and edge technology both. And then it includes the multimedia support system also, and the TV streaming also. Then 3.5G, which is from 2006 to 2010, it is like HSPA, and this service is basically on 3G network with enhanced speed and more mobility. Then comes the 4G network. Then it is like basically the WiMAX or LTE or Wi-Fi network. After that, it is 5G network, which is now expected to be implemented in India by 2019, but it is due to Corona, everything get delayed. So the test bench has been ready. You all should know about that. The 5G network, government of India has built a test bench with IIT Kanpur, IIT Madras, and Samir Kolkata is working with this. So this test bench is created, and we have our indigenous 5G network also. So now the 5G promises, like, it will be higher gigabytes. Then we can see a 4K screen, which is like 3D videos we can play. And then we can see a augmented reality, which is a very much real virtual reality, very much inclusive with a virtual reality. Then it can be utilized for self-driving car, and then it can be connect thousands or millions of IoT networks and hubs. And then it will be like utilized for street light cameras for smart cities. So these all things, like capacity enhancement, ultra high reliability, low latency, and massive connectivity, these all happens in 5G because it is working at higher frequency ranges. If it is going to higher frequency ranges, the bandwidth increases, and if the bandwidth is increases, the channel capacity is increases. As you all know about the Shannon-Fanon theorem, and that channel capacity C is equal to bandwidth into 1 plus SNR. So this is like, if we are increasing the bandwidth of the system by increasing the frequency operation of frequency, and then we can increase the channel capacity. And if the channel capacity increases, then we can connect to the massive IoT network, or we can enhance the channel capacity. and then we can make a low latency also. As the channel capacity increases, the data rate is also increases, and so the delay will decreases. So it happens to be a low latency architecture. Now, what is the difference between 5G and 4G network? Basically, a 4G network, the latency is much higher than 1 millisecond. Then data trafficking is about 50 exabytes per month. Then peak data rates are like 20 Gbps, and the available spectrum is 30 gigahertz. So as you can see that it is increasing very high. The 5G has transformed everything. As you can see that, as I have told earlier also, we are increasing the frequency. If we are increasing the frequency, the channel capacity increases. The channel capacity increases, then the data rate is also increased. So everything is correlated with each other. So here, as you can see that in 5G it is 20 Gbps, and in 4G it was 1 Gbps. So the connection density also increases. Here only 100,000, like 1 lakh devices can be connected. Here like 10 lakh devices can be connected in a square kilometer. So this is the basic difference between a 5G and a 4G. And now what is the change in the architecture or a system design? We have to see that thing. So now if we are comparing it in the speed of downlink speed of different technical generations, as I have told earlier that 3G, 3.5G HBA is there, then 4G LTE is there, then LTE category 4 is there, LTE advanced is there, and then 5G is there. So in the 5G, the data downlink speed is 1000 Mbps. So it's like 10 times. It's like 10 times of the LTE advance. So the requirement is high frequency operation and high bandwidth. So whatever the circuit we have to design, those circuits should have able to design for higher frequency operations, which can withstand with the higher bandwidth. So now the 5G, 6G network is also coming in the picture. That as we are increasing the frequency range, if we are increasing from 95 gigahertz to 3 terahertz, it like in the 6G range. So for this higher frequency range, the basic implication is the data rate is 1000 Gbps. So it sounds very attractive, but the issue with higher frequency is like absorption and attenuation. In the atmosphere, if we are increasing the frequency, the atmosphere will attenuate the signal and the signal strength goes on decreasing. So we have to make a power amplifier which can withstand or which can throw the signal in a very high power, so that the signal can travel from one place to another place with a satisfactory amount of degradation. So degradation will happen, but the degradation will be more than the less than the your threshold degradation, so that the power will be transmitted, the power of the signal will be transmitted easily from one end to the another end. So this is the basic problem with the 6G network, as it is working with 95 gigahertz. So it will be like it will absorb, means the atmosphere will absorb, and length wavelength of this a higher frequency will not be so higher. It will be very small, so it will get absorbed in the atmosphere, and the attenuation problem is there. But the prospects of 6G is like we can connect a large area with a higher data speed, and we get a satellite based communication in terrestrial network or non-terrestrial network coverage. So this is the basic fundamental of 6G network, which is booming around. Now we will discuss about the architecture. Before going to that architecture, we have to see that in 5G, cost efficiency, mobility, continuous connection, latency, peak data rate, cell edge data rate, and cell spectral efficiencies are there. Now, the connections is like we have a massive MIMO. Massive MIMO means multiple input, multiple output. So, various numbers of antennas, array antennas are there, which is like if the number of antennas increases, the speed is automatically increase. Getting my point? So number of element, number of power dissipation increase, number of packet size also increase. This is the issue with the 5G network. So as the network is a bigger network, we have to multiple antennas to target different type of subsystems or connection subsystems. So for that, the number of these networks element will increase. So these network elements also give some power dissipation. Now if we are seeing the energy budget and the loss, in that we can see that the basic loss is due to the power amplifier, which is like 50 to 80%. So the basic in a BTS terminal, base terminal station, the basic power loss is done due to the power amplifier. So making a best suited power amplifier to reduce the power losses is the target or the research question for nowadays researchers. So basically how they can do it, they can do it by simply reducing the power level, by reducing the linearity, means resolving the linearity issues, by resolving the efficiency issues. If the power amplifier is highly linear, so the harmonic power loss will be reduced sufficiently. And if the efficiency of the power amplifier is very high, then the input power loss or the output power loss will reduce drastically. So these two things are very much important for the power amplifier. One is your your linearity, another one is your efficiency. So these two targeted parameters we have to see for the power amplifier. So basically power amplifier is power hungry circuit which requires a lot of power to transmit from one end to another end, and for during this transmission they give the power loss, drastic power loss, like 50 to 60% of power, base power station loss. So now after seeing this, we have to go for a basics, that how to design a power amplifier. So before going to that, first we should know about the transistor and the diode basic. That in a transistor bilateral current flow can be happen, but in your diode it's like unilateral. Okay, so one question is that why we are seeing the transistor or a diode? Because every transistor is working as a switch in your switched mode power amplifiers, or a switched mode power amplifier like class C, class F, class G. So for that reason, I am discussing about these things. So now, what is switch? Switch is like we should when it is off, then total current should be in off and the voltage should be higher. This is the ideal waveform, but we didn't get a ideal waveform. This is the practical waveform which has some delay time, which has some fall time, which has some rise time. So this is the issue, means this in this condition the power losses happens when it is in transition mode. When a signal is in transition mode, then only the power losses are increased. So now in if we are seeing this or replicating it in through diode, the best thing will be the rectifier. Rectifier is also work as a switch. So now switch and a rectifier, if we are telling, like we should need this type of architecture, like in off state no current should flow, in on state full current should flow. But ideally we didn't get in a diode based rectifier. We get a curve, like exponential curve increasing and a off stage curve. So this is due to the semiconductor use. If we are utilizing a semiconductor where both the models like drift model and the diffusion models are working, so current is moving from one electrode to another electrode, like from cathode to anode. Then drift diffusion models are implemented, then only the current can move. So for those reason, this non-ideality behavior come. So for this non-ideality behavior, the power losses comes. And if we are seeing in a switch, which is a transistor based switch, ideally we should need a straight line with increasing of gate bias. But practically we didn't get that one, because the transistor works in three regions: cutoff, saturation, and linearity. So these three reasons is implicated in the practical loss. So here we can see that here it is unused current at that particular voltages. So this creates a power loss in the transistor level design. So basic power loss starts from the initial transistor based design only. Then when that transistor is utilized for a circuit, again other power losses will happen. So the power losses are cumulative in nature, means from transistor level power losses are there, in circuit level power losses is there, in system level power losses are there, and every power losses are cumulative in nature. So the last or the final result of the power amplifier will be higher in nature. Hello, hello, is I am audible? Hello, hello, hello. Yeah.
Yes,
Yes,
sir,
yes.
you are audible.
Yeah. If any doubt is there, kindly ask me. If any doubt is there, kindly ask me. These all are basic in nature. Whatever I am telling. Now we will deal with, as we are going in the RF circuit design, we have to know about the S parameter. As we are dealing with the RF circuit, we cannot see the voltages or current by simply shorting and opening it, because the frequency of the input frequencies are very high. So at that high frequency we cannot short and open, short and open. So electrical parameters like H parameter, G parameter, Z parameter, Y parameter, ABCD parameter, those parameters are not utilized for RF circuit design. We utilize S parameter, which is known as scattering matrix parameter. Scattering matrix parameter means we are seeing the input waveform, incident waveform, and the reflected waveform or the transmitted waveform. That's it. These three waveforms we see in the node. If it is S11, if it is S11 means we are getting the reflection, we are getting the reflection at the port 1 only. And if it is S22 means reflection at port 2. If it is S21, that is how much power wave has been transmitted from one port to another port. If it is S12, how much power is reflected back to the reflected back to the port 1 from the port 2. So these are basically reflection coefficient. We calculate reflection coefficient from this, and the waveform is represented as A and B. So B1 is the reflected output from the port B1, and B2 is the reflected output from the port 2. So now we are seeing B1 is equal to S11 A1 plus S12 A2, and then B2 is equal to S12 S21 A1 plus S22 A2. So this is like matrix based design. Now S11, what is S11? S11 is input reflection coefficient, just how I have told, with the output matched. What is output matched? That whenever we are designing any RF circuit, remember that we are always matching the circuit with 50 ohm. So 50 ohm matching, because the output of the antenna is we consider as ideally 50 ohm matching circuit. So whenever we are saying that this is matched with something like some circuits output, then we are telling that the output of that particular circuit is 50 ohm. So S11 is input reflection coefficient, S21 is forward transmission gain, S12 is reverse transmission or the isolation. For switch we see the isolation, and then S22 is output reflection coefficient with the input match circuit. Now if we are comparing it with S parameter and the your voltages, then we can simply write that S11 is equal to V1 minus I1 Z1. This is the basic formulas by which we are calculating the S parameter. This is the relationship between the S parameter and the voltage and current waveform. Now the stability comes in the picture. I should ask, have you heard about stability? Hello? Anyone? Have you heard about stability? Hello? Why the
Yes,
circuit
sir.
should be stable? Why the circuit should be stable? Hello? Hello? Is I am audible? Hello?
Yes, sir. Audible,
Yes,
audible,
yes,
sir.
sir.
Yeah, yeah. Anyone? Any student? Any faculty? Hello?
For better performance, sir.
Yeah?
For
Means
better
what?
performance.
No, why we are seeing the stability means how you can designate a system is stable or not.
How we need to check?
Yeah. How you can check the system is stable or not, and why we are seeing that system is stable or not. Why we are checking it?
If the output is constant, then we can say it is stable.
It's not like constant, as we can see that if a circuit is a stable or not, because when we are designing a circuit and then fabricating that circuit and making that product to a given targeted frequency, like I have designed a circuit of RF transceiver, and I am claiming that it should work in 2.4 gigahertz or 5 gigahertz. So like we are targeting an ISM band. So a thumb rule is that your simulation should have 10% extra, 10% extra of stability. Means if you are saying that you are giving a 2.5 gigahertz to 5 gigahertz circuit, then your output means your system should have stable for 1 gigahertz to at least 7 to 8 gigahertz. This is the range. When you are doing a simulation, you have to see that your system should be stable from 1 gigahertz to 8 gigahertz. Then only you can claim that your system, while fabricating, after fabricating, it will be stable at 2.5 gigahertz to 5 gigahertz. This is the thumb rule. When you are designing any circuit, we have to be very cautious that the simulation results should be far better at higher frequency ranges. Getting my point? So now, hello, everyone get my point?
Yes, yes, sir.
Yeah. So now how to make a stability, now how to analyze the stability. basic concept is, if we are designing a Smith chart based circuit, no stability circle should come inside the Smith chart. If any stability circle comes in the Smith chart, then your system will not be stable at that condition, or at that power levels, or at that frequency levels. So this is mandatory to make the system stable. Every stability circle should be outside the Smith chart. If suppose while simulation some stability circle come inside the Smith chart, the thumb rule is that if it is coming from the left hand side, you have to put a resistive network in shunt. If it is coming from right side, then you have to put a resistive network in series. So this is the thumb rule. Whenever you are designing a circuit, you have to take care about the stability first. Means if we are designing a circuit at particular range of 5 gigahertz, your system should be stable for in simulation from 4 gigahertz to 6 gigahertz. Okay? Hello? Hello?
Yes, sir. Yes, sir.
Yes, sir.
Fine, sir.
Okay, so this is the thumb rule. Means whenever we are designing anything, we have to see for every aspects. Now the other aspect is like how to make a system design. Means to make a system circuit in a stable condition, you have to add some other circuits. Then by this only you can see that when we are designing a power amplifier, we are adding various types of circuits. Like first is your biasing circuit is required, then your matching circuit is required, then your stability circuit is required. So matching circuit, it should be in input side also, output side also. So input matching circuit, output matching circuit. Then for that matching circuit also some stability circuits are required, and for output matching circuits also some stability circuits are required. Then we require a gate biasing or a drain biasing. Both biasing should be different, because the gate driving capability are different. Like if we are using a enhancement mode, the gate drive at 1 volt or a 2 volt, but whereas the drain is biased by 28 volt or 48 volt, like that. So both the circuits are different. So biasing, for making the biasing circuit also stable, you need a stability circuit. So it's like means by integrating several circuits, you come up with a large circuit which is known as power amplifier circuit. Getting my point? Means power amplifier circuit is a system which comprises of your power amplifier design, your input matching circuit, your output matching circuit, your stability matching circuit, your biasing networks for gate and drain separately. So these all come up to make a power amplifier circuit system. Getting my point? For this reason only, the power amplifier is individually a whole chapter. Means you cannot complete it in a small talk. It's like a whole lecture course. Means you need about 40 to 50 slide, means lectures on the power amplifier only. So it's a very vast subject, as it is comprises of various types of circuits. So it's a vast subject, and it's very much interesting also, as we are seeing the circuit, and as we can see that there is a lot of scope of research in the power amplifier design, because the basic need of user based network is like to reduce the power hungriness. So power for reducing the power hungriness of a power amplifier, the power amplifier should be linear in nature, and the efficiency of a power amplifier should be higher. So these are the basic concepts. Yeah. So as we know this stability criteria, this is the old stability criteria, which is basically depend on the evaluated by the S parameters. Now power transfer, as the power transfer theorem is there, like for transferring the power from the input side to the output side, the both the impedance should be matched. First thing, impedance matching should be there. If impedance matched is there, then the maximum power transfer can be happen. Okay, so now so power transfer versus load resistance. If we are increasing the load resistance, then at particular time the power will be matched, and then power get on decreasing if we are increasing the load resistance, because it is unmatched, because after this it becomes unmatched. So the power will be, maximum power will not be transferred. The maximum power will transfer only when the load impedance is matched with the source impedance. Okay, so now in this reflection coefficient, a reflection coefficient is also due to mismatch of impedance. Getting my point? You can means, if we are physically thinking about reflection coefficient, you can think like two pipelines are there. Mechanically I am making an analogy of a reflection coefficient, is like two pipelines are there. One pipeline thickness is 2 inch, and another pipeline thickness is 5 inch. What will happen? The extra water will spill out from the 3 inch, remaining 3 inch. Getting my point? Hello, hello,
Yes,
hello.
sir. Yes, sir.
Getting my point means 2 inch pipe is there and a 3 inch pipe is there. 1 inch is remaining, means it is not matched. It is not matched. The water will spill out from that 1 inch. Getting my point? So this is the basic phenomena which can be seen. This is also only known as how much it is spilling out from that port. How much power is spilling out from that port is resembled by the reflection coefficient. So we determine the reflection coefficient by gamma. So it is basically gamma is equal to load impedance minus source impedance divided by load impedance plus source impedance. So now no reflection will be there, so maximum power transfer will happen. So unity current gain frequency, you all know that 0 dB means your gain is 1. When current gain is 1, then only it is 0 dB, because dB means 10 log 10 log power gain or 20 log power gain. So whenever it is 1, then only the dB will be, as it is a logarithmic of 1 is equal to 0, the dB will be 0 dB. So now we come up with the small signal model. As you all know that the small signal model is basically CGS, CGD, RDS, CDB. These all things we determine in the small signal model. Now for the calculation perspective, we are calculating the omega t, from which we can calculate the ft, means the transit time, means the this ft means the current unity current gain frequency. So by calculating the omega t, we can calculate omega t is equal to 2 pi ft. So from there ft can be calculated. Then a resistive termination, if a resistive termination has been given, then the current to current power gain will also reduced. So now if series shunt feedback is there, then it will increase, the output impedance will be increased due to the series shunt feedback. As this feedback is kept here, we can change it in basis of your Miller concept. The impedance can be shifted to the output side. So by shifting it, we can calculate this value. Then the common gate structure, basically this gate structure is basically utilized wherever we required a matching circuit, means input matching circuit. We go for common gate structure. If we are requiring a matching or a buffering between the two circuits, we always use common gate structure. Okay. Now the basic utilization of common gate structure is impedance matching, broadband input matching, no passive components, then power consumption, and the power transfer independent of power consumption. So now inductor degeneration structures are also there. Then inductor degeneration means we are giving a negatively feedback inductor. We are not placing a resistor here, we are placing a inductor here. Then by placing a inductor, what we are getting, that the input matching of this is very good with the previous one. Now the effective transconductance is also higher. Then the input quality factor is increasing as we are using a inductor in the negative feedback mode or a degeneration mode, source degeneration mode. So the power will be stored and a Q factor will be determined. Now the power transfer of ID structure will be like various type of parameters, like reflection will not be happen. For this reason the S11 is equal to 0, and then the gain S21 will be higher. Okay, so now the gain, if we are trying to calculate with the voltage and the current, we can calculate it. This was with the help of S parameter, this was without the S parameter analysis. And then the power consumption, if we are going to state that how much power consumption is there, we are always taking it in the saturation region. So we are utilizing the saturation equations here. So we are utilizing a transistor in a switched mode methodology. Switched mode means cutoff or saturation. Getting my point? There is no linearity. For this reason, in the ID equation, it is a saturation equation. Okay. Now the power consumption, the technology is constant, the minimum feature size, then the mobility, there is a problem with the mobility at the higher electric field, the mobility degradation happens. And then the standard specifications are source impedance and carrier frequency, and circuit parameters are LG, LS for source and gate degeneration inductance. Now summary, impedance matched at carrier frequency, applicable at to wide band applications, like if S11 is less than minus 10 dB, it will be utilized. Then power transfer, it is only transfer the power at narrow band because it is an inductor. So the impedance will be vary with the frequency. For this reason, at higher band, it will not be matched. Means the impedance will not be matched, because all you know that XL is equal to omega L. So at higher frequency, if F is increasing, the impedance of the inductance will change. And if the impedance of inductance is changed, then what will happen, that the matching or the power transfer will not able to take. So increase in GM also, and the power consumption is very large due to in the gate side it is there. Now we come to the our today's topic, which is the power amplifier outline. Till now, is there any issue with anything? Hello, all participants.
No, sir.
Yeah, means,
It's going on.
Excuse me, sir.
yeah, please.
Sir, how this ID structure is applicable to wideband applications?
No,
Like
it
you
is
have
narrowband.
in the
It is
previous
narrowband.
slide.
I have told here only the power transfer. It is used for narrowband. It is not for higher band. I am just telling that how many type of input impedance matching networks are there. Means like common gate is there, then ID structure is there for input matching only.
So
Yeah.
my question is that you have written in the slide that impedance matching is there and it is applicable to wideband application. But if we are resonating it at a single
No,
frequency,
no.
then
Wideband
how
there.
it is applicable?
No. If it is the S11 is less than minus 10 dB, if we are reducing the S11, like suppose that your input is changing, variable input is coming. Getting my point? So the reflection at the port of 11, which is coming from the baseband signal, is reduced to minus 10 dB. Hello.
Okay. Okay.
Then at that time, the impact of frequency, which is XL is equal to omega L, is very less, because the inductor is working as a resistive load at that S parameter. At that S parameter, when the reflection is very less. Getting my point? Means reflection is very less means you have a matched circuit. Then only this reflection will come very less. It is a very less reflection. When we are purchasing some RF instrument, we are just checking the reflection should be less than minus 10 dB.
Sir, that is okay.
So
But the
reflection
thing
is
what I
very
want
less.
to ask-
So the matching is proper. If the matching is proper for a wide range, if we are getting a wide range matching, getting my
Sir,
point?
how we will get a wideband matching using
Yeah,
a ID structure?
it's not
That is
like
my
simply.
point.
Yeah, it's
Because-
not
Excuse
actually.
me, sir.
Yeah,
Excuse me.
it's not like
Because
XL is equal to omega L. This is
because
the
if you are using LS and also you are using LG, that is the gate inductance and the source inductance, and you are matching it with the gate to source capacitance, it will be matched at a single frequency.
yeah.
Either we will have to apply some other input filter circuit like T type or
No. Hello.
Yeah.
Hello. This
Yes, sir.
narrow band, this power transfer will be at narrow band, and the
Yes,
wide band
right.
application means I am talking about the higher frequency application, like 5 gigahertz or a 10 gigahertz application.
Right.
Ultra
right.
wideband applications are there, na? But
So, for
the band
ultra
is
wideband-
small. Getting my point? Means if I am talking about a 10 gigahertz, but the band is of 100 megahertz, frequency is 10 gigahertz. The bandwidth is 100 megahertz.
Okay.
Getting my point?
So that
Hello.
Yeah.
Frequency is 10 gigahertz. For this reason, wide band I have written 10 gigahertz, but the bandwidth is
You are-
100 megahertz. For this
Okay.
reason, I have written narrow band power transfer.
Okay, so
Getting
you are
my
saying
point?
that wideband application means if I am talking of 10 gigahertz or 28 gigahertz or 60 gigahertz, that is a wideband application. Is it so?
Hello.
Yeah. Hello.
I am talking about higher frequency. But for narrow band.
Yeah,
It
for
will
narrow
be-
band application.
Yeah, narrow band. For this reason, here I am written the power transfer is narrow band.
No, so
Hello.
that is fine. That is fine.
Yeah, and
For narrow band
this
power
is
transfer, it is
applicable for wide band application means higher frequency application. Means like
Higher frequency only.
Yeah, higher
Wideband means
frequency
higher
application.
frequency, you mean to say?
Yeah, hello.
Yeah. Okay.
Network is
Okay,
not
sir. Thank
not
you.
good.
Thank you.
Hello. Can you
Yeah,
get
yeah.
my point? Means higher frequency, but the band is narrow band. Hello.
Okay, sir.
Yeah.
Thank you.
Yeah. So now we come to the power amplifier outline. Here, the continuous power amplifiers like class A, class B, class C power amplifiers, and the switched mode power amplifier, which are much more utilized in the base station, like class E, class F, class J amplifiers. So the linearization techniques which are utilized like feed forward, Cartesian feedback, pre-distortion, polar modulation, then outfacing, and the Doetry power amplifier. So now we will see one by one that what are the trade-off between in the output power and the voltage swing. First, if we are utilizing a common emitter stage, then we can see that the impact is like the impact is like if the load is realized as the inductor, then the drain will be voltage will be lower. Then we can introduce the inductor as a current source for sourcing the for biasing the circuit. We can utilize a inductor. As in practical way, we are utilizing a tank circuit, which is a parallel inductor and capacitor circuit, or a bias T for biasing the circuit. Now, effect of higher current: if the output transistor is chosen wide enough to carry the large current, then its input capacitance is very large, making the design of the preceding stage difficult. Then we deal with the issue of interposing. Means like taper stages are there between the up conversion mixers and the output stage. Then another issue arising for higher current, AC current in PA, relates to the parasitic packages. If we are dealing with this, parasitics is due to whenever we are putting a IC inside a die, then we are making it connected with a bond wire. So bond wire itself has its own parasitic in nature. Then the higher, the large current can also lead to a high loss in the matching network. After that, the power amplifier characterization begins with the two generic tests of non-linearity based on unmodulated tones, intermodulated modulation, and compression. And then, as you all know, that the harmonics we are determining by Volterra series. And we are utilizing that Volterra series to see that how much harmonics, means like third harmonics or a fifth harmonics or a seventh harmonics or a ninth harmonics, is affecting the power level. So we are always seeing the full power level. If it is a 6 dB, it's good. And then if it is a 1 dB compression point, then it will be fine for us to design a circuit. Now, a RAP model means AM/AM conversion or a AM/PM conversion is there, means the amplitude phase or amplitude conversion is there. There one RAP model has been utilized to generalizedly see the non-linearity of a power amplifier, which is basically depend on the voltages, input voltages and the output voltages basically. So this is the basic formula of the RAP model, which utilize for the dealing with the static non-linearity, which comes in the integrated power amplifier design. Now, if the power amplifier is a single stage, which is not possible, if it is a single stage, typically, ideally, we will get a good connection with the antenna directly. We can connect and then we can see that. But the drawback is half the transmitter power will be wastage, because we cannot make the power amplifier itself is a differential mode, and we have to put a balloon. Balloon means balanced input and unbalanced output. So which will impact in the balloon introduced losses, which can be a core loss or any magnetic loss. So now, then the second drawback of single stage, single-ended power amplifier. What is known as single-ended power amplifier? That the output of the power amplifier will be single one. Okay, so the drawback stems from the large, very large transient current that they pull from the supply to the drain, and then it is transformed. So this will be impacting various nodes, that if it is a single-ended, the matching network is required, which again introduces a losses. Then if we are going for a differential power amplifier, then in differential power amplifier realization, one thing is good, that we reduce the common mode noises. Whatever the common mode noises are there, we reduce it. And then the use of power amplifier eliminates both the voltage and the gain and the package parasitic issues. The power amplifier must still drive a single-ended antenna, which is, again, we have to introduce a balloon here to connect the single-ended antenna. Now, the classification of power amplifier, like continuous is class A power amplifier. As you all know that the efficiency is 50% of class A amplifier. Then the class AB amplifier is there, B amplifier is there. The B amplifier, basically it just invert the output input to the output, so we are getting a conduction angle of 360 degree, and which we can utilize. And then we are getting a good efficiency regardless of the class A amplifier. Here we are getting a good efficiency of about 78.5 or 79%. Okay, so now the class C amplifier is there. Then there the conduction angle is further reduced, and in order to avoid the large harmonics in the antenna, the matching network must provide some filtering circuits also. The transistor delivered the less power to the load. Now the class C amplifier is also approaching towards 100%, but it cannot be 100%. If we are plot a conduction angle versus power output power, it's like at 360 degree we are getting ideally a 100%, but we are not getting a 100% efficiency at any time. So now in the with harmonic enhancement, if we are suppose some harmonic, we are introduces so many structures here, so many circuits here, so it will introduce some harmonics inside the class A amplifier. Now class E amplifier stages are non-linear amplifier. It is basically a non-linear amplifier that achieves 100% efficiency approximately, which while delivering a full power. The basic issue with this type of class E amplifier is the linearity. So linearity is very, very, very poor for this switching power amplifier logic. Okay, so now because the M1 sustain a lower voltage when it carries the current, and M1 carries small current which is sustained with a finite voltage, the transition time between the on and off are minimized. So the dealing with the finite input and output transition, the gate of the output device must be switched as abruptly as possible to maximize the efficiency, but the large output transistor typically necessitates the resonance at the its gate, inevitably receiving a linearly sinusoidal waveform. Now class E amplifier ideally it gives a finite input and output transition time, but the transition, as you can see, the transition is very, very high. And I have told earlier also, in the transition only the power come into picture. So now three conditions are required for the class E amplifier. One is, as switch turns off, Vx remains the long enough to for the current to drop to the zero. Vx and ID1 have non-overlapping waveforms. The first condition resolve the issue of finite fall time of the M1. Then Vx reaches zero just before the switch turn on. The second condition ensures that the VDS and the ID of the switching device do not overlap in the vicinity of the turn on point, thus minimizing the power loss. Then the variation in Vx and dt is also near to zero, which the switch turns on. The third condition lowers the sensitivity of the efficiency to violate the second condition. So now the class F amplifier, what is the change in this class F and class E is that basically the class F amplifiers is that amplifier which is a switching stage. The output load network provides a high termination impedance at the second and third harmonics. The voltage waveform across the switch exhibits sharper edges than the sinusoidal, thereby reducing the power losses in the transistor. And this type of, the basic concept is to give a high termination impedance for the harmonics, means the second and third harmonics. So we are not getting a simple sinusoidal, we are getting like this type of waveform. So now for cascode, if we are putting a two transistor, then it will be a cascode in the configuration. Like in the first transistor gives a this transistor gives the protection to the V in the input transistor, but the overdrive is a issue with this, means the output swing is reduced because we are using a again transistor here, so it will decrease the threshold by its own threshold. Now large signal impedance matching, the simplicity model and the practical model. The basic simple model, what we are saying, that we are just putting one capacitor there, but actually there is some resistance path is also there. So the situation is more complex. By introducing this one resistance, the situation becomes more complex because the resisting path always provides a output voltage, means the power will be gone from the resistive path. As you all know that in the form of heat is equal to H is equal to I square RT. So the resistive path will always heated and it will always dissipate the power. Now for large signal impedance matching, then the simple case is when we are not taking the resistive path and we are only taking the class CBD1. We are only taking the CBD1. We are not taking the resistive path. This is the simplest case. Okay, so now how to measure the, while we are measuring the power amplifier, how to measure? We are designing something, we are fabricated something, but how to measure? Basic measurement tool is load pull measurement. In this load pull measurement, we are putting the impedances in imaginary and real part, and then we are plot the contour of the optimized impedance, which can be tuned. So we vary Z1 says that the power delivered to load impedance remains constant and the equal to the P1, thus obtaining the contour, and then next we seek those values to of Z1 that yields a higher power output power. So this here we can see that this P1 is the higher, but we are going for P2 because it is more stable. Okay, so now we are going for a linearization technique. How to linearize our circuit? There are various types of process are there. One is your feed forward process. This is opposite to the feedback process. It is a feed forward process, means it's make a parallel path. So for this, the feed forward process suffers various shortcomings. The analog delay element introduce losses if they are passive in nature, or distortion if they are active in nature. The loss of the output subtractor degrades the efficiency. The linearity improvement depends on the gain and phase matching of the signal sensed by the subtractor. So whatever the here the subtractor is sensing, based on that it is matching the circuit. So here comes another trade-off. As we are going for a higher linearity circuit, it decreases the efficiency of the circuit. So we make some optimization. Then comes the Cartesian feedback circuit. This, if the power amplifier output is down converted and compared with the baseband signal, as the error term proportional to the non-linearity of the transmitter change can be created, with quadrature down conversion, this is called as Cartesian feedback. Then Cartesian feedback avoids the output subtractor and is much less sensitive to the path mismatch, but requires some linearity in the power amplifier. Then comes the pre-distortion circuit, means we are adding some more circuit with the power amplifier. If the power amplifier non-linear characteristics are known, if we know that the non-linearity comes at which frequency or which power levels, then we can make such that the pre-distortion, means the signal will be pre-distorted and then it is feed to the power amplifier, and then we are getting a straight line. If we are comparing these two waveforms, we will get a resultant of a straight line. Yeah, this is the basic concept, that whatever the transfer characteristic of the power amplifier, we know the same inverse transfer characteristic will be designed, but it has a drawback. The performance degrade if the power amplifier non-linearity varies with the process, temperature and load impedance, while the pre-distortion does not track these changes. Getting my point? Means the PVT issues are not tracked by the pre-distortion circuits. Then the power amplifier cannot be arbitrary nonlinear, as no amount of pre-distortion can correct for an abruptly nonlinearity. Variations in the antenna impedance somewhat affect the power amplifier nonlinearity, but pre-distortion provides a fixed correction. So once you have designed this, it cannot vary. So variable pre-distortion is much utilized. Now then the envelope feedback. The envelope feedback is tracking the AMM conversion of the power amplifier and then going for the resultant result. Then envelope detection can be done by the mixer also. Then the mixer can be designed by the source follower circuit. The slew rate is chosen much less than the carrier slew rate, so that the output tracks the envelope but not the carrier. So in practice, the limiter may require two or more differential circuits. So as you can see that by introducing the envelope carrier with a limiter, the circuit gets more complex. So now after that, the polar modulation is there. In this polar modulation, what we are going to give, one is two path we are going, means the input is passed through the two path. One is from limiter, one is from envelope detector, and then it is feedback to the power amplifier, switching power amplifier. This approach is called as polar modulation because it processes the signal in the form of magnitude component and the phase component. Then the combining the operation is typically performed by applying the envelope signals of the supply voltage of the output stage with the assumption that the output voltage swing of the function Vd. Then more realistic, it will be like partial realization of EER will be there. After this, we have some issues. First issue is the mismatch between the delays of the envelope and the phase path corrupts the signal. The second issue relates to the linearity of the envelope detector. Unlike the feedback topology in the slides, envelope feedback, the polar transmitter relies the precise reconstruction. So precise reconstruction is a big issue with this polar modulation. And then we come to the issue of poor definition, that we are only increasing the envelope detector so that whatever the variation due to the process, due to the temperature, due to the voltage or power levels should be tracked easily by the power amplifier, and that should be given to the power amplifier, so that the power amplifier at any condition, at any PVT condition, it does not corrupt. Means the transmitted power, whatever the calculated transmitted power, the same transmitted power should be given to the output. So the circuit becomes bigger and bigger to make the power amplifier more and more linear. So now if we are seeing that amplitude signal is going down, by masking it is increasing. So now the other issues are like the inductor. Whenever we are designing an on-chip inductor, the area is very high, and then the two inductor whenever are kept side by side, then the mutual inductance is also plays a big issue. Then the outfacing will come. This is the basic concept and initial concept for the power amplifier to be matched. This type of power amplifier here, as you can see, that two power amplifiers are used and the signal is separated, and then the output voltages is there. As you can see, the envelope of the input and the envelope of the output is same, but the amplitude is higher, as it has to be deliver a high power. So the issue between two power amplifiers are like we are utilizing it as a summing device. So it can be like two power amplifier react differently for different temperature or power levels. So for those also it's a biggest issue. Then the interaction between the power amplifier, that outfacing with a transformer, if as you I have told earlier also, that one balloon is there. Balloon means unbalanced, balanced, unbalanced output. So now, so now the cancellation techniques are there. Uh, hello, hello.
Yes, sir. Yes, sir.
Yeah. So Dohetry is also there. So if any issues are there, you can consult me. Dr. Rao. Hello.
Yes, sir. Yes, sir. Tell me. Tell me.
Yeah. Can I complete the slide, because I have to go?
Oh, okay. No, no, no problem, sir. No problem.
Yeah.
You can
So
conclude, sir.
yeah. So for conclusion only, I just want to say that different type of techniques are there for feedback and for increasing the linearity. Those techniques should be seen and implemented while doing the simulation only. After simulation, you have to come up with some good results which can be then performed in the circuit level. And I request all to go for a Google Skywater 130 nanometer technology. They have a free shuttle technologies also. You can go come up with your own IC if they accept your design. So I refer all to go for the Skywater 130 nanometer for Google. It's free PDK. You can download it and you can make the circuit in any tool like freeware, ngSpice, or anywhere. Getting my point? Hello.
Yes, yes, sir.
Yeah.
Yes, sir.
Thank you all for joining the session. And if any queries are there, kindly contact me or mail me. I respond in the mail frequently. Yeah.
Thank you, sir. Thank you for sparing your valuable time. Thank you so much for this
Yeah.
informative section.
Yeah. Thank you.
And if our audience will face any doubt, then they will contact you via mail.
If any internship related thing is required, they can come up with mail me directly, or they can visit my lab website, so it will be better.
Sir already dropped his official ID in the chat box. So you, dear audience, you may use this ID to
Yeah.
contact sir. Thank you, sir. Thank you for
Yeah,
this informative
thank you.
session.
If any doubt is there, kindly give a mail. I will try to resolve it. Yeah. Thank you all.
Thank you, sir. Have a
Thank
nice
you,
day.
Dr. Raut. Yeah. Have a
Ladies
good day.
and
Yeah.
yes, sir. Thank you. Same
Thank
to
you,
you.
sir.
Well, ladies and gentlemen, now we already are at the end of session number 10, and again we will meet at session number. We will meet for session number 11 sharply at 8:30. Sorry, 11:35 a.m. So kindly, if you want to leave, you may leave. The link, I think, the attendance link, I think it is shared. Yes, the attendance link is already shared. So please use the link and give your attendance and feedback. And at 11:35, we will again meet for the session number. Yeah, for the session number 11 at 11:40 a.m. Thank you all. Thank you all for your cooperation till now.